Good evening, everyone. If you wanted to know if and how a compiler can silently introduce vulnerabilities, this talk is for you. It was titled the way it is because the ultimate aim of bug finding is to somehow match human capabilities to do so. I'll not keep the suspense simply because, let's face it, a fuzzer today is no match for a human in terms of writing tests that would ultimately discover vulnerabilities. But it can definitely slowly get us there. At the moment, it can still flag interesting corner cases that make my colleagues sometimes go, "Oh wow, I hadn't considered that." And these are people who are developing features and writing tests for it, so that is something I would say. A quick summary of my talk if you're feeling a bit impatient already. One of the first steps in creating a security testing framework is to define the threat model. In other words, what are the class of bugs we are interested in finding that pose a threat? For us in the Solidity compiler team, it is mostly those bugs that result in incorrect code generation. A compiler is not only expected to translate a high-level program to a low-level one faithfully, but also optimize it for optimum resource usage. Now, we can tolerate unoptimized resource usage sometimes. It's not a critical threat, but it is a critical threat if it produces incorrect code. To catch bugs that result in incorrect code generation, we use semantic fuzzing framework. Using this approach, we have found 22 bugs, and we continue to deploy this approach for early bug discovery. We continue to use this approach for early bug discovery. And I'm glad to share that virtually no Yul optimizer bug has been found post-release in the past 2 years, thanks for the most part to fuzzing. About me, I'm a security engineer in the Solidity compiler team in the Ethereum Foundation. Most of my work revolves around using current testing frameworks to find security critical bugs in the Solidity compiler, hopefully before the compiler is shipped to end users. Let's get started. The compiler, like I said, is a program that translates a high-level program into a low-level machine code. In the case of the Solidity compiler, the input program is a Solidity smart contract most often, and the expected output is the Ethereum virtual machine bytecode shown on the right side. And in the process of getting there, the compiler essentially parses the input program, converts it into an intermediate representation, and optimizes that representation as much as possible before basically bringing it down to the machine level by means of assembly. So it has these four high-level components inside it. The Solidity compiler actually comprises two largely semantically equivalent code generators. One is IR based. IR stands for intermediate representation. Please note that I'm going to be using the terms IR and Yul interchangeably because Yul is the name of the intermediate representation that Solidity uses. So the new IR-based code generator that has been recently marked for production use is shown on the top, and the legacy code generator that has been in use since the early release is shown at the bottom. The main difference is that the legacy code generator directly converts Solidity program into a bytecode representation and optimizes it, whereas the IR-based code generator first brings the Solidity program down to the Yul level and thereafter works at the Yul level in the process of optimizing and assembling the code. As I mentioned in the summary slide, our threat model is not the compiler user or the programmer, but bugs silently introduced by the compiler itself. And this could be any of the three components: optimizer, code generator, or the assembler. Parts of bugs are specifically out of scope for the purpose of this presentation, but we do use a fuzzer to continuously find parts of bugs by means of continuous testing. And these most often look like internal compiler errors. Now, this slide is targeted at those of you who may not be familiar with fuzz testing. In a nutshell, fuzzing is the process of feeding random mutations of an initial set of test inputs to the program under test until it crashes or you have a sufficient assurance that the program has been well tested. As simple as it sounds, traditionally it has been very effective at finding vulnerabilities, most often exploitable vulnerabilities. So what you see on the slide is a simple while loop which runs until eternity unless you quit using Control-C. And in each iteration, a random program is generated, a random input, is generated, and this input is fed to the program under test. And usually there is some sort of runtime monitoring to check if the program ran correctly or not. There is a caveat though. I said random input generation is very effective in general, but it's not really well suited for compilers. The main reason for this is that most mutation or changes to an existing test input render it unparsable. For example, if we would randomly mutate the smart chord tract shown on the left, which is syntactically well formed, assuming that do something actually does something syntactically meaningful, most often custom off-the-shelf fuzzers would mutate it at the byte level and make the program unparsable, for example, by messing with the function keyword or the public keyword. And this is quickly rejected by the parser. This is a problem because our main intention is to find code generation bugs, and you cannot find code generation bugs without having parsable programs. So to summarize, what we need is an approach that understands what a valid program looks like and generate such a valid program using some form of structure awareness. By structure awareness, I mean having a sense of what program language grammar looks like and what a semantically valid program means. In the next few slides, I'm going to outline our approach. We approach input test program generation in two different ways. Initially, we took the protobuf approach, that is using the protobuf library written by Google to generate program specifications that are eventually turned into a test program. Later, we felt that this introduced an additional dependency, that is, we had to essentially compile and build the fuzzer against libprotobuf and libprotobuf mutator, two externally shipped libraries, and we decided to write the Solidity program generator from scratch. And this is the new input generation strategy that we're using. The advantage is that we don't have any external dependencies and it's written purely in C++. Now, finding a bug requires a reference point, which we don't have. Remember that an incorrect code generation bug is only deemed to be incorrect if we know what is correct, but we don't have a reference for what is correct. To solve this problem, we employ differential testing. So what we do is we have two arms, so to speak, a baseline and an experiment. This could be, for example, unoptimized and optimized code, or legacy and IR-based code generators. Now we test both of them on the same input at the same time and see what they do. If they do the same thing, then they're doing it correctly. If they don't do the same thing, then one of them is wrong. And this is flagged as an incorrect code generation bug for manual triage later. Now, to find out what they're doing, we use execution tracing. And largely this means that we make use of an EVM client to monitor the state of the program during execution, or the Yul interpreter. I'm going to get to each of these things a little later. Now, about the input generation, I told you that we have a fully fledged C++ only Solidity program generator. Essentially what this does is each iteration it generates a random semantically valid Solidity program and feeds it to the component under test. That's essentially what it does. The Yul input generation is based on the protobuf approach, which I outlined in the previous slide, and this is slightly more complicated. It involves 3 steps. First, we write a specification in the protobuf language. This contains a fundamental unit called a message, and it allows us to build a bottom-up specification of the language, wherein, for example, we can define a basic block to be a set of statements and upwards a program as a set of basic blocks. For those of you who are interested, the full specification is linked below. Step 2 involves generating protobuf messages based on the encoded specification. For this, we use libprotobuf mutator. Essentially, this library is a generator of protobuf messages conforming to the specification we have custom written. In text form, a generation looks somewhat like the JSON inputs shown below. We may have, for example, a block of statements which consists of a single if statement whose condition is the equality operator over a variable reference and 0. The final step involves translating the protobuf message into a valid Yul program. This translator or a converter accepts a protobuf message and converts it to a Yul program. In this slide, I provide an example to visualize the 3 steps. So essentially, the JSON input is converted to the text form of the Yul program, which looks like if x0 equals 0, where x0 is a predefined or a pre-declared Yul variable. This is, of course, a code snippet. The entire program is much larger, but I just wanted to demonstrate what the conversion may be visualized as. All of this is encapsulated in this block diagram. So we have a protobuf specification. We generate instances of protobuf messages based on using libprotobuf and libprotobuf mutator. We use the converter program that we've written to convert these specifications into real test programs. The next question is, how do we know if there is a miscompilation or an incorrect code generation bug? To do this, we simply employ differential fuzz testing, as I hinted in the previous step. This mainly involves 3 steps. Step 1 would be to track side effects of execution. We have some infrastructure to do this. Using this infrastructure, we run the baseline and experimental programs and compare side effects. If the side effects don't match, there is a bug. Most often they match, so there is no bug. Bugs are often very rare, sort of 1 in a million or 1 in several hundred thousand iterations. Now, to actually perform execution tracing or to monitor side effects, we use either an EVM client like EVM1 or the Yul interpreter. Specifically, Solidity programs target or drive EVM client, and the Yul programs drive the Yul interpreter. So essentially, in each of these 2 input generation strategies, you have a test program that's being generated. We take that test program, put it to an execution tracer, and see what the program is actually doing at runtime. And using all of these components, we can summarize the fuzzing setup shown in the slide deck. So we have a program generator. We have 2 different ways of generating programs, which I briefly summarized, and a differential testing strategy, which involves feeding this program to a baseline and an experimental component under test, using an execution tracer to actually understand what is happening at runtime, and comparing this trace to see if there is a bug or not. Now I summarize what we've achieved in this project so far. So let me begin with a couple of example interesting bugs. Bug 1 has to do with incorrect keccak computation. What you see on this slide deck is a simple smart contract that contains a single function called f. The function returns a Boolean value called ret. It contains only assembly code. The assembly code writes the 32-word 0 to memory location 0. It then computes the keccak 256 hash of the first 32 bytes, stores it in a variable called a. It then computes the keccak 256 hash of the first 23 bytes, stores it in another variable called b, and returns the Boolean value a equals b. That is true if a and b are equal and false otherwise. Question is, what should the function return? Are they equal or not? What actually used to happen, and this is the buggy execution, was that the function used to return true. And this was because the compiler assumed that keccak 256 is always computed over memory regions that are multiples of 32 bytes in size. That is 32, 64, 128, 96, so on and so forth. Based on this assumption, the compiler would cache pre-computed keccak 256 values based on the start pointer, assuming lengths rounded to 32 bytes were equal of two different computations. As you see in the slide before this, the first computation has a length 32 and the second 23. So if you were to round 23 to the nearest multiple of 32, that would match the previous computation. And this is incorrect because keccak hash over 23 zeros and over 32 zeros are two different values. Now the bug fix is obviously to add the additional safety check wherein the cached value is only used if the start pointer and length match exactly. Now you can understand the motivation for the caching itself. It was to save gas because computing a keccak hash is resource intensive. So if it's already been computed and a subsequent computation is identical, can be guaranteed to be identical, it saves resources. But in this case, it turned out that that was at the cost of correct computation, which is the main job of the compiler, which is to produce correct code. The second bug introduced that I'm going to demonstrate that is found by the fuzzer is somewhat more subtle. To demonstrate the bug, here we have three Yul functions. Remember, Yul is the intermediate representation used by the Solidity compiler. The function readValue returns the value stored in EVM storage slot 0. The function writeValue writes 2 to storage slot 0 and returns this value, that is the value 2. The function bug performs a multiplication of the value returned by writeValue and 1, the value 1 left shifted by the return value of the function readValue. Please note that the opcode SHL, that is shift left XY in Yul, means Y left shifted by X and not the other way around. Another important note is that Yul promises left to right evaluation. That is, expressions are evaluated from left to right. Now the question is, what should the return value of the function bug be? We can work it out together. So the main computation in the bug function is the multiplication, which can be simplified to mul of 2, which is the value returned by writeValue. Please note that we are evaluating left to right, and therefore writeValue is first evaluated, followed by shift left of 2, 1, that is 1 left shifted by 2, which is the value 4. This simplifies further to mul 2, 4, that is 2 multiplied by 4, which is 8. That is the correct value that should be returned by the function bug. Now, before I demonstrate the buggy optimization that led to an incorrect computation, I should introduce you to the optimization rule that simplifies this function. And this is that if we have two expressions x and 2 raised to the power y which are multiplied, this is identical to x left shifted by y. And hence the left hand side of the equation could be simplified to the right hand side. The main advantage, of course, is that we are saving a multiplication and potentially saving resources and definitely saving gas by eliminating multiplication. So we could optimize the program by applying this rule. When we do it, the program looks like this. Note that the function calls on the right hand side have been reordered. So read value appears before write value. And also note that we are evaluating from left to right. So if we were to simplify this, what would happen is we would evaluate read value first, which would return 0 because it's not been returned to, and the right value would return 2 as before. This means 2 is being left shifted by 0 bits, which is equal to 2. Clearly 2 and 8 are different values, and this is why the fuzzer flagged this as a bug, and this was actually an important bug and something that was easy to fix by adding a safety check. That is to say that apply the optimization only on expressions that do not have any side effects. If they have side effects, simply do not apply the optimization. Of course, we would compromise optimization at the cost of correctness, and that is a no-brainer. The main goal of the compiler, like I said, is to produce correct code, even if we were to occasionally miss optimization opportunities. The next few slides, I'm going to summarize the results that we found using this approach at a very high level. So if we were to look at the bugs that were found by the fuzzer by component, most of them were bugs in the Yul optimizer. And the good news here is that all of these bugs were found before the Yul optimizer transitioned from experimental to production. So this had very little impact on end users because the component was specifically marked experimental release. So use at your own risk. The second highest number of bugs were found in the legacy code generator, followed by the new IR-based code generator, which was also marked experimental at the time and hence had little impact on end users, followed by the optimizer rule. Now, the only security critical bugs that had a severity rating had to do with bugs in the optimization rule. That is, when the rule was unsafely applied, that is, sufficient safety checks were not carried out, or the rule itself was wrong. Fortunately, the majority of the bugs were found in experimental features if we look at bugs by impact, and did not affect smart contracts that use stable features. The bugs we found in production components were quickly patched. And maybe the highlight is to say that 3 bugs were found in unreleased features, so they were even fixed before it saw the light of day, so to speak. If one were to break down the bugs down by their severity, you would find that most of them have a low or a very low severity rating. Only one had a medium severity rating. This is either because they're easy to detect during regular smart contract testing, or that they require a series of prerequisites to be fulfilled for the bug to manifest itself, and satisfying all these prerequisites in most cases is a bit far-fetched. And reason the majority of the bugs, like more than 80%, are not applicable severity because these bugs were found in experimental features, and by definition, we did not categorize bugs in these experimental features as security critical because they're not marked for production use. A few key takeaways from our experience. 3 bugs were found by the fuzzer even before a PR was merged. This is great news and validation that continuous fuzzing bears fruit. Also, more importantly, fuzzing helped transitions the Yul optimizer safely from experimental to production use. 15 bugs were found before production release. This means 15 fewer bugs that users would encounter. Finally, we noticed 0 bug collision with the bugs found by the fuzzer and external users. This poses the question if the fuzzer is actually finding bugs that are meaningful to end users, and whether these bugs would actually affect real-world deployed contracts at all. I would leave this as an open question because this is out of the scope of the talk today. Let me shed light on what we're currently doing. Now, some of the recent work focuses on trying to make the fuzzer generate more human-like or intentional test cases, kind of ties back to the idea of the title of this presentation, Can the Fuzzer Approach Humanness? And this is because of the insight that 2 of the bugs that were recently found by the fuzzer were not directly exploitable, but it needed the assistance of my colleagues Hari and Daniel to actually demonstrate that they can be exploitable and are actually potentially security critical bugs. So the question is, can the fuzzer approach humanness? Can it kind of approach the kind of things that my colleagues were doing to understand if the bug is exploitable? Finding a solution to this is tricky because pure randomness is ill-suited, and short of training an AI, we don't have a means to understand what is human or intentional code. But a few heuristics could be used, which I can quickly demonstrate using a concrete example. We have an optimization pass called the redundant memory store eliminator, whose job it is to eliminate redundant stores to memory. Now, it requires either a read location to be equal or not equal to the write location to perform two different functions, to eliminate or not eliminate write to memory. Now, pure randomness will most likely lead you to the not equal part than equal. That is, most often fuzzers will synthesize a write to a location that's arbitrarily different than the read location, and very rarely exercise the equality path. This could be solved by a heuristic that we read from location that is already written to occasionally, and this can already help us bridge some gaps in purely random testing. This is some of the work that we're currently doing. Yeah, that brings me to the end of this talk. Before I conclude, I would like to highlight some key takeaways. In this talk, I highlighted our continuous grammar-based fuzzing approach for early bug discovery in the Solidity compiler team. This has proved to be quite useful to test security-critical components of the compiler, specifically to find miscompilation or incorrect code generation bugs. While it does not contain or provide formal guarantees, there is evidence that it works, so it is very practicable. And the other nice thing is that it can be continuously deployed. I mean automatically deployed in a continuous integration setup, and that works quite well. So we are reasonably happy, but at the same time, because of no formal guarantees, it is my day job to continuously monitor the kind of programs that the fuzzer is generating, and to essentially ensure that we don't miss security critical bugs, especially in newly developed features, so on and so forth. Yeah. I thank you for your patience. Thank you for attending the talk, and I'd be happy to take questions now.
All right, we actually have Bhargava online with us. So can you hear us?
I can hear you. Can you hear me?
Yes, we can hear you too. So we have two questions from the floor. So first, what are some of the factors that affect the performance of fuzzing on Solidity and common ways to optimize for performance?
Some of the factors that affect the performance of Solidity fuzzing are the latency of compilation itself. Please bear in mind that the compiler parses the input, translates it into an intermediate representation, and then optimizes it and then assembles it. So it's a pretty big pipeline. Sometimes it can have multiple seconds of delay. And for fuzzing, this is a bottleneck. Some ways to optimize it would be to focus fuzzing on specific portions of the compiler. For example, we have a fuzzer that targets the optimizer specifically and skips the, let's say, the generic parsing and the code generation part. So we use strategies like that. Yeah, that's one way to answer the question.
Okay. Next question. Do you think we'll ever reach a time where we do not need to use the fuzzing anymore?
Yeah, this made me chuckle. I'm not sure, to be honest, because, programs are quite complex in nature, and we humans are prone to make errors and make mistakes. And as much as we invest time in code reviews and thorough testing, there are always corner cases that can escape the human eye, or a test case that's not sufficiently well written. So I feel we'll probably need to use fuzzing for some time to come. Yeah.
Yeah, I agree as well. All right. Thank you very much for your time, Bhargava.
Yeah.
Hope to see you soon next time.
Thank you.
Yeah. Round of applause, please.
Hope so too.